So here is the data. Mu naught, mu1, 2 Borel probability measure. On RD. And then I am going to consider a new set. I start with the following. Let gamma be a measure on RD cross. Yeah. So it will have maybe better to say let mu not be a measure on x, mu1 be a measure on y, and write x, y here. So consider the two projection, pi naught. This is a projection from RD, cross RD to RD, defined by pi naught of xy is x, and pi 1 from RD, cross RD to RD. This is the projection defined by pi 1 of xy is y. And I am going to push gamma, use pi naught to push gamma. So pi naught is defined from RD to RD. Gamma is a measure on RD to RD. If I push gamma using pi naught, I'll have a measure on RD. So the measure of A is by definition gamma of A cross RD. So in probability, this is going to be called the first marginal of gamma. Also, pi 1 is a measure from RD, cross RD to RD. Gamma is a measure here, so you can push the measure here to obtain a measure on RD. Pi 1, push forward gamma of B equal to gamma of RD cross B. This is for A, subset of RD, and B, subset of RD. And you say that that is the second marginal of gamma. If mu naught is the first marginal of gamma, and mu 1 is the second marginal of gamma, we say that gamma has mu naught and mu 1 as marginals. And to be more precise, I should have said gamma has mu naught as first marginal and mu 1 as second marginals. We write, it is convenient to write gamma is in gamma mu naught and mu 1. And the people refer to this as a transport scheme. So we have a transport map, and here we have a transport scheme or a transport measure. So the cost by Kantorovich, let C from RD cross RD to 0 plus infinity be lower semi-continuous. So this means nothing but, what I mean here is the set C is less than lambda is closed for all lambda real number. And I have imposed that C is greater than or equal to 0. What is important is C is bounded below. And so I chose the bound to be 0 here. Now a new functional. The cos counter of gamma is the integral over RD cross RD. C xy gamma dx dy. And Kantorovich problem is okay. So before I write the problem, I would like to say that the core focus of Kantorovich is not to prove that this problem has an infimum, because as we will see soon, it is trivial from the calculus of variation point of view that this problem has an infimum. What Kantorovich made is the remarkable foundation, which is a duality result, which I'm going to state later. He looked at this problem, and he identified the dual of that problem. And once you identify that dual, I would say a lot of things which is known in the current mass transport theory, you can derive that from the duality. So I am going to spend about 4 to 6 hours trying to prove that duality result. So problem, easy. Does the infimum C k over gamma mu naught mu1 has a minimizer. Fundamental and hard. How do we characterize the minimizer of CK? In other words, the question I am asking here is, I give you a gamma which is in this set, and I ask you, tell me whether or not it is a minimizer. Let me turn this problem to a familiar case. Assume I have a function on the real line. Assume I have a differentiable function, and I give you a point x, and I ask you, does this point minimize the functional? So you can compute the derivative. If it is not 0, you say it cannot be a minimizer. If it is 0, you still don't know. It may be a maximizer, it may be a local minimizer, or neither. Okay, so the derivative at s negative 1 will be 0, whereas s negative 1 is not a minimizer. So the question which is asked here is, can I give a necessary and sufficient condition which, if I check it, will tell me I have a minimizer? And that fundamental result is a statement of duality. So let me comment on the existence result. We need to know the following fact. So let me start with a definition. No, I will not. I will not do that. Otherwise, I am going to repeat. I am going to define later rigorously what weak convergence mean, and so let me be vaguer here, and in 30 minutes I will come back to a rigorous definition. So here is a proof of existence. I am given two probability measures. I have this property. Remark. Just the condition, just this condition, tell me that gamma of A cross RD is mu naught of A for every A subset of RD. In particular, if I take A to be RD, I see that gamma of RD cross RD is 1. And so anything here is a probability measure. When you take the set of Borel measure, so if I take the set M, this is the set of gamma Borel measure on R capital D. So I am thinking about the case capital D equal to 2D. And you look at the total variation. This set is compact for the weak topology. I have not defined what is a weak topology. I'm going to define it later. Okay. So in fact, it is compact, mean gamma n converges weakly to gamma, mean the integral of f d gamma n converge to the integral of f d gamma for every f which is of compact support and continues on RD. And this remark I am making that this set is compact, this is a particular remark of a stronger result saying that if I take a sequence of measures such that the supremum gamma n of k for each k compact so for each k compact I compute the supremum over n. So this number is a number depending on k. If this supremum is finite for every k, then I can extract a subsequence which is weakly convergent. So in particular, if the total mass is less than 1, then this is immediately satisfied. And so the comment I made earlier is just a particular comment of that more general result. Now, take a minimizing sequence. Such that the limit n go to plus infinity, c cantorovich gamma n equal to the infimum of c k. Because of this property, I can assume, without loss of generality, passing to a subsequence if necessary, I can assume that gamma n converges weakly to gamma. It is better that I think this is the notation which is usually adopted. If C was continuous and of compact support, I will be done. Right? Because the limit n going to plus infinity, the integral over Rd cross Rd of C d gamma n, I want to know if it is bigger than the integral over Rd cross Rd of C d gamma. And if I have this lower semi-continuity property, I'll be done. So if C was continuous of a compact support, then I'll have equality. However, the assumption which is usually made is C is lower semi-continuous. It is well known that if C is lower semi-continuous, for arbitrary C, define C epsilon of x of z. So here z is sy. To be the infimum, the distance between z and w divided by epsilon plus c of w. The infimum over w is in Rd. So we are going to see later that this function is Lipschitz and of Lipschitz constant 1 over epsilon, provided that this infimum is finite everywhere. And for instance, if C is bounded below, that is enough to guarantee. Now, assume in addition C is lower semi-continuous, then the infimum is at 10. Because of the following property, if I take W equal to Z, you see that this is less than C of Z. And so C epsilon is less than C of Z. Now, if you take a minimizing sequence for epsilon fixed, you'll have Z minus Wn over epsilon plus C Wn is less than C of Z. Assume that C is bounded below. It is like not replacing this by a constant. And I see immediately that the norm of Z minus W will be less than C of Z minus a constant by epsilon. And so if I take any minimizing sequence Zn, it is automatically bounded. If it is bounded, since we are on Rd, and so we are on a bounded subset of Rd, the set is pre-compact. We can extract a subsequence which is convergent. If C is lower semi-continuous, Wn converging to W, C of W will be less than or equal to the lim f of C of Wn, and so you have a minimizer. So if C is a lowest semi-continuous, I just claim that in this expression I have a minimizer, and this helps making some computation. So let us come back to our problem. C was just lowest semi-continuous. I approximate C by Lipschitz function, in particular functions which are continuous. There is one problem I have not resolved. I have not resolved the fact that C epsilon is a compact support. So here is how you resolve that. I am going to multiply C by a cutoff function. So I am going to take a function which is 1 when I am in the interval negative r plus 1, r minus 1, and which is 0 when I'm outside negative r. So I multiply C of Z by phi r of Z, and I integrate d gamma. This is less than the lim f C epsilon. The lim f of C epsilon of Z phi r of Z d gamma n. Sorry, it is equal. So it is equal, therefore it is less than or equal to. Because now I have a continuous function which is of compact support. And if I use what it means that gamma n converges to gamma weakly, I get that inequality. But let us not forget that C epsilon is smaller than C. And phi r is less than or equal to 1. So this is less than the lim f. The integral of C of Z d gamma n. Now, I am going to erase what is in the middle. And I let R go to infinity, and I use the Lebesgue-dominated convergence. Then I let epsilon go to 0. I use the Lebesgue-dominated convergence. And on the left-hand side, I have a C of Z. D gamma is less than this. And so we have a existence of a minimizer. Okay, so let me state a fundamental result. So this means Monch-Kantorovich theory. Theory. Yes. So I am not going to state the best result because this duality result over the year has been improved a lot, and you can work on a Polish space. You can work with very general function. Let me just state a result in RD, but I would like to say that the general result is, there is a more general result than stay in RD. Let C from RD cross RD to 0 plus infinity be lower semi-continuous. And again, this means that the sub-level set of C are closed. Now construct the following sets. Let UC be the set of functions of UV such that UV from RD to negative infinity, infinity are upper semi-continuous. So upper semi-continuous means negative U is lower semi-continuous. And you have the property that U of x plus V of y is less than C of xy for every x, y in RD. So in the general theory, people will consider C from x cross y to 0 plus infinity, lower semi-continuous. So x and y are topological spaces, and U of x plus V of y will be less than C sy for every s in x and every y in y. Let mu naught, mu1 be two Borel probability measure. On RD such that so when I write C of xy gamma ds dy, this is the functional I want to minimize. And I want to exclude the case where the functional is identically plus infinity. So I want to impose some condition on mu naught and mu1, which is going to guarantee that. And I'm imposing a too strong condition. Okay. So the set of gamma, which has mu naught and mu1 as marginal, contain the product measure. Okay. So it is not empty. One can check that the product measure has mu naught and mu1 as marginals. So I am going to make the strong assumption that the integral C xy mu naught of x, mu naught ds, mu1 dy over RD cross RD is less than infinity. So that guarantee that my cost function is not identically plus infinity. Then here's the result. Then the infimum over gamma having mu naught and mu1 as marginals. The integral over Rd cross Rd of C d gamma equal to the supremum over uv in C, the integral over Rd of u d mu naught plus the integral over Rd of v d mu1. And once you have that, if I was going to admit that we have this, then I will save 1 week, of course. This result is due to Kantorovich in a simple situation, but its generality has been proven by Nog and Smith.
I got a little bit lost here. So before you were showing this law semi-continuity, right?
Yes.
Of the respect to the measures, right, of the function of C. And so so you were just to give me an idea of in that C epsilon before.
Yes. So
the idea would be to take the epsilon to 0 after that and R to infinity.
yes, if you take R to infinity and yes, epsilon to 0, you use the Lebesgue dominant. You use the, for instance, Fathou's lemma. It tells you that Fathou's lemma tells you that this converges to the integral of C of Z if I let gamma d gamma. If I let, I can take epsilon equal to 1 over R. If I take R to infinity, it converts to C of Z d gamma. And I will have proven that this integral is less than this limit f, which is my infimum. And so I have proven the existence of a minimizer. Yes, gamma is a minimizer.
And then here, in this fundamental result, you introduce this other U and like splitting this other space UC, right?
Yes, UC is a set of pair of function.
This set of
pair of function.
Pair of.
Yes, UC is a set of UV, and UV are functions.
Yeah, this is the new ingredient that they introduced. This splitting, like seeing two functions or find this set of functions. You see. Is there an idea of why it's important to introduce this UC?
Oh, yes.
Before getting into the UC question, I have another question on that part. The minimizer, doesn't it depend on R or epsilon? Because the existence of the minimizer is based on the fact that the cost function is continuous and...
No. So I said f of C Kantorovich is the limit of C Kantorovich gamma n. Right? I take a minimizing sequence. Since gamma n are probability measure, so I need to check that this set is compact. I haven't proven that, but this set is compact. Gamma n is here. So I can extract a subsequence which is convergent weakly. Now, I come here, and I use the fact that these functions are continuous of compact support. So I can write that this is the limit, the integral of CR, C1 over R, Z, phi R, norm of Z, d gamma n.
Yeah. This is the, you insist that easy part. You have insisted some place that this is the easy part of the this is not the easy part.
That is the easy part.
This is part.
Existence of a minimizer.
This could escape mass to the infinity when you pass the limiting gamma into gamma.
No. Because, yes, mass cannot go to infinity.
Yes.
Because you remember mu, gamma of A cross RD is mu naught of A. Now take the complement of the ball of radius R. If I write the gamma of the complement cross RD, this is mu naught of the complement of the ball. But this measure is fixed, and when R becomes large, this becomes smaller. So I am controlling the fact that when the S component becomes large, the set on which I am is a set of very small measures, and so mass cannot go to infinity. Right? Because this is a set of the limit, this goes to 0 as R goes to infinity. And I do the same thing for the second component. Okay. So this is the proof. I was saying that I didn't prove that this set is compact, but this is the proof of complexity. When you want to prove that it is compact, you prove that not only mass doesn't go to infinity, but you keep the same marginals.
So why was it important to introduce this C epsilon then?
Because otherwise, if I didn't have C epsilon, that is not true.
For C?
Yes, for C, that is not true. Because C is lower semi-continuous. I didn't say C was just lower semi-continuous. So C epsilon make it continuous. Okay, so let me briefly comment on this magic duality. So in the calculus of variation, there is a duality theory. And usually when you read a book on the calculus variation, it looks very boring with the duality theory, and you wonder what you want to do with that. And in fact, the result which are stated in the book has been so overused that when you have a new problem, it doesn't help you. So what I mean is, for what this result can be applied for, it has already been intensively applied for. So most problems you are going to encounter, the duality result which are there will not help you. However, there are some miracles which occur. So duality says, if I have this, that, and that condition, then I have duality. And usually, when you are working by yourself, some conditions are not satisfied, and you still want to check that you have duality. No theory is going to guarantee you that. You are going to check by hand. And this is a case where you check by hand that you have duality. So let me give you the rough idea. I want to minimize C Kantorovich of gamma under the condition gamma is in gamma mu naught mu 1. Set G infinity of gamma to be 0 if gamma is in gamma mu naught mu 1, infinity if gamma is not in gamma mu naught mu 1. So when I say it is not, I am saying it is a measure, but it doesn't have mu and nu as marginals. I can remove this constraint. So let me write this as gamma is a measure on RD cross RD, but it doesn't have mu naught and mu 1 as marginal. So I can write that this is the infimum over M RD plus RD Ck of gamma plus G infinity of gamma. Okay. So I have turned the constraint into a new functional, and I can minimize on big set. Every duality result I know of, this is what it is. Nothing more, nothing less. Now, you need to express this. You need to find an explicit formulation of that. So, let us look at this constraint. Okay. So the fact that the first marginal of gamma is mu naught is telling me that gamma of A cross RD is mu naught of A for every A. So if I rewrite this, it is telling me that the integral over RD of the characteristic function of AD mu naught is the integral over RD cross RD of the characteristic function A of x gamma dx dy, right? This is that, that is that. So saying that this holds for characteristic function, since every function can be written as a combination of characteristic function, this is equivalent to this whole for every function. And so these two conditions are equivalent. Okay. Now, the condition gamma of RD cross B is mu 1 of B for every B can be written as the integral over RD of V of y mu 1 dy is the integral over RD of V of y gamma ds dy for every V. Okay, so I am going to use these two conditions to write G infinity. So look at the following. The supremum over UV, the integral over RD cross RD of U of x plus V of y gamma ds dy minus the integral over RD, minus plus U of x mu naught dx plus the integral over RD of V of y mu1 dy. I claim that this functional is G infinity of gamma because of the following reason. If gamma is here, then this integral is equal to that integral, this integral is equal to that integral, and so this difference is 0. If gamma is not here, it means that either this equality is violated or either that is violated. Assume that the first one is violated. If it is violated for u naught, it is violated for lambda u naught for every lambda real number. The functional is linear in u, therefore the supremum must be plus infinity. And so this proves that G infinity of gamma equal to that. Okay, so in the calculus of variation, this is what you do. No matter what else you do, this is what you are doing. You can write it in different way, but this is what is hidden behind that. So, yes? Yes, we can do that. But let me say one word because I have written. Now, plug this G infinity, substitute data here. Then you see this functional appearing. And you see data appearing with gamma. So when I put these two together, I will have f over gamma sup over uv, the integral of c of xy minus u of x minus v of y, gamma dx dy plus the integral of u d mu naught plus the integral of v d mu 1. So you apply the minimax theorem, and this is the first time you are doing something not rigorous. You apply the minimax theorem. When you apply the minimax theorem, the infimum over gamma of this is negative infinity, unless this is non-negative. So this is how you get that condition. You get that condition to prevent that the infimum is negative infinity. So when this is greater than or equal to 0, gamma is non-negative, you can remove it, and you are left with that functional, which is what is there. And this is your duality result. Okay, I'm going to stop here.